All right, ladies and gentlemen, today's class recording has started. So, this unit that we're going to start in on today deals with electricity and magnetism, which I think I mentioned to you last week is, generally speaking, kind of more traditionally a physics concept, but it's important that we understand atomic structure before we can understand electricity. And so we learned about atomic structure, what an atom looks like in different parts of an atom, and I hope that this chart, to start off, looks familiar to you, okay? You don't have this chart, okay, on your outline, but I do hope it looks familiar. Couple of things. One, we talked about that the electron, when we look at its relative mass, right, much, much, much smaller than protons and neutrons. And this third column right here, we talked about the idea that this is what we refer to as relative charge, right? Whenever we refer to something as relative, what does that mean? What are we doing? We're comparing, right? Not necessarily measuring, but comparing. And so we talked a lot about the idea that electrons and protons have positive charge, or sorry, electrons have negative charge, protons have positive charge, right? And when we have a neutral atom, or a atom in its natural state, the number of protons and electrons is the same, right? Because it has no charge. So, on your outline, right, electric charge comes from what? Electrons and protons, and generally speaking, electrons and protons are two types of what? Subatomic particles, right? So electric charge comes from subatomic particles. Okay? And we are sort of doing this in reverse of the way that it was discovered naturally through scientific investigation and through experiments. A lot of people knew about electricity before we knew about the structure of an atom. And in fact, knowing electrical concepts and the idea of attraction and repulsion and stuff like that helped us to figure out what was actually going on when we look at experiments like the cathode ray tube experiment or the gold foil experiment. It's important that we understand those ideas of attraction and repulsion, even though we didn't know what was actually going on. But now we realize that electric charge and the things that happen because of electric charge are based on subatomic particles. So, charge, we say, is quantized. And quantization is a word that we were introduced to before, whether you remember it or not. But it's the idea of that there are definite values, definite limits to what can exist. So, charge is quantized. There is a minimum amount of charge that can exist. And that minimum amount of charge is the charge of one electron. All right? An electron is a piece of matter. And that means that we can't have less than an electron. Technically, that's not true. If you learn more about the structure of matter, we learn that protons, neutrons, and electrons are actually made up of smaller things, but that's beyond the scope of what we're doing right here, right? So, underneath electric charge and quantized, right, there's a minimum amount, and that minimum amount is the charge of one electron. And all the charges that we measure are some integer multiple of that one electron, right? So we can have the charge of 2 electrons, we can have the charge of 3 electrons, or we can have the charge of 87 electrons, but we'll never find a charge that we can measure that's equal to 14.25 of an electron. It just doesn't work that way. Charge is contained in these subatomic particles, so we can move the subatomic particles around, but we're always either going to move the whole subatomic particle or none of the subatomic particle, not portions of it. Okay? Good with that? And we determined the charge on one electron through a pretty famous experiment by a guy named Robert Millikan, who did something we call the oil drop experiment. I'm not going to explain it to you at this point. It's beyond the scope of what we talk about. But through his experiment, he was able to deduce or measure the charge of one electron as negative 1.6 times 10 to the minus 19th coulombs. This capital letter C is the unit that we use to measure charge, and it's a coulomb. And we spell it like this, if I remember correctly. Hold on a second. I always forget how to spell it. It's French, and there's O's and there's U's, and I can't remember which one goes which way. So let me check real quick. Alright. C-O-U-L-O-M-B. Alright. So the coulomb is the unit for charge. We use capital C to represent coulomb. It's the same unit whether we're talking about positive charge or negative charge, right? Just depending on whether we have protons or whether we have electrons. Okay? Good for starters? Okay. So, charge is another example of a conserved quantity. What do we say? What do we mean when we say that something is conserved? Saved. It stays the same, right? Charge depends on protons and electrons. Protons and electrons are matter, and matter is conserved. Therefore, charge is conserved. We might be able to move electrons around in a situation from one atom to another, but at the end of the day, if one atom is going to gain some electrons and gain negative charge, somewhere else another atom has to lose electron and lose negative charge, so that the amount of total charge in a situation has to be the same, right? The concept of conservation doesn't change, we just apply it to charge, and specifically to electrons and protons. The number of electrons and protons in a situation is always going to be the same total, even if they move around from one to another, all right? And if we take a look at this picture, which you guys actually don't have a copy of, but, right, here are pictures of 3 different atoms, okay? On the left-hand side, we have a neutral lithium atom. If you know that this is a neutral lithium atom, what do you know about it, or what has to be true about it? Alec. Negative and positive charges are equal. If you know, do you remember, what number do we look at to figure out the actual number of protons and electrons? The atomic number. Do you know the atomic number of lithium offhand? Okay, so anybody know the atomic? It's 3, all right? So up here in this picture, might be a little hard to see, but there are 3 positive protons. Those are the red circles here, okay? And then there are 3 negative electrons surrounding it, okay? There's actually 4 neutral neutrons in there, but that doesn't contribute, okay? So, if we go from picture A to picture B, what has happened to our lithium atom?
It's an isotope.
It's not an isotope. It's an ion. Ions and isotopes are 2 different things, okay? So, it has become an ion because, Joe, what actually happened to it? It lost an electron. Where did it go? I don't know at this point. It's not important, okay? But this species right here, right, it's not an atom anymore, it's an ion, all right, because it doesn't have the same number of protons and electrons. It has more protons than electrons. Therefore, what kind of a charge will it have? It's a positive charge. It has 3 positively charged protons, but only 2 negatively charged electrons. So overall, it has to have a positive charge. That electron, let's say it was this one right here, because that's what it looks like from the picture, it had to go somewhere. right? Charge is conserved. It didn't just disappear. It's probably on some other atom somewhere. And we'll talk about why that happens more in the next chapter that we talk about. Sammy, go ahead. Very much so, yes. What we find out, Sammy, and we'll talk about this today, is that valence electrons are, generally speaking, well, depending on what kind of atom you talk about, in metals, valence electrons are not held very tightly to their nucleus. And so it's actually pretty easy for valence electrons just to sort of leave. And we'll show that that's what contributes to the behavior of metals here, and that's what makes them behave in a certain way. But yes, definitely that's a valence electron. Okay? And then over on the right-hand side over here, this doesn't happen very often in nature, and usually it won't happen by itself. Okay? But if we go from picture A to picture C, okay, we've picked up an electron. Now there's 4 electrons, but there's still only 3 protons. So that one on the right-hand side would have what kind of a charge? It would have a negative charge. It has more electrons than protons, right? And so when we talk about things gaining a charge or becoming charged, an object becomes charged when it has an imbalance of subatomic particles, right? If it has more electrons than protons, it's going to have a negative charge because it has more negatively charged electrons than positively charged protons. If it has more protons than electrons, it's going to have a positive charge. All right, okay with that idea for starters. Okay. I'm going to change gears. I'm going to jump down a little bit because we're in this mode right here, and so we're going to skip part 2, Roman numeral 2 of this thing, and we're going to drop down to Roman numeral number 3 and talk about methods of charging. So this slide tells us that an object will become charged when it has a different number of electrons than protons. So let's talk about how that happens. All right? So, charging, or methods of charging. Okay? An interaction between objects results in an imbalance of protons. Oh. Sorry about that. All right? So, some interaction causes an imbalance of protons and electrons. Okay? When that happens, and this will be more important when we start talking about bonding in the next unit, but when that happens, what we see is that electrons are the particle that moves around. Objects don't trade protons. They will trade electrons, though. And when they trade, both objects end up with a different number of electrons and protons. Some object gains electrons, and if it does, it has a negative charge. But if some object is gaining electrons because of conservation, some other object has to be losing electrons. And the object that loses electrons is going to end up with a positive charge. Okay? Which object gains electrons, which object loses electrons, all depends on the materials that are involved. Okay? Really depends on what we're talking about. So some objects are very ready to pick up electrons and gain negative charges, but some objects really want to lose electrons, and they'll end up with positive charges. It really just depends on the nature of the materials that we're talking about. Okay? So, how does this happen? So, a couple different ways. First, charging by friction. Okay? I think all of us are pretty familiar with friction, right? Right? You know, right? Two objects move past each other, right? Friction is a force. We know that friction causes things to heat up as we move along, right? Turns mechanical energy into heat energy. For somebody who's asking me to round their grade, maybe we should pay attention a little bit more, just throwing it out there, right? But because it's a force, it causes things to happen. In this case, we've probably seen this example before, right? Okay, something that happens at a birthday party sometimes, right? You rub the balloon on your hair. As your hair moves across the balloon, or as vice versa, as the balloon moves across your hair, the friction between those two surfaces causes electrons to move. This is obviously a simplification, but over on the right-hand side over here, this is like a close-up of one strand of your hair and the surface of the balloon. Okay? They both start off with balances of protons and electrons. But as the balloon moves across the hair, the balloon wants to pick up those electrons because of what it's made out of and the kind of material that it is. The hair is ready to lose those electrons, again, because of the material that it's made out of and what properties that material has. So these electrons end up jumping from one object to the other object. Okay? As a result, what charge does the balloon end up with? Negative charge. It's picking up electrons. But if electrons are jumping from the balloon or to the balloon, and the balloon ends up with a negative charge, what has to happen to the hair? It has to end up with a positive charge. How big of a positive charge will the hair end up with compared to the negative charge of the balloon? It's got to be the same because of conservation, right? The balloon can't pick up more electrons than the hair loses. Okay? And I think all of us know as a result, if the hair ends up with a negative or positive charge and the balloon ends up with a negative charge, what happens? They attract each other, right? Opposite charges will attract each other, whereas like charges do what? Repel each other, right? Okay. I think that was actually up in Roman numeral number 1, letter E. I think probably most of you probably could have filled that in, but if you didn't, Roman numeral 1, letter E, number 1, like charges repel and opposite charges attract. Okay? So, something that you saw the other day in your lab, but just to show you it again, so we can talk about the next part. Okay. All right. So, oh, that's a terrible picture. Let's get the whole thing in there. All right. So, this object right here, it's a little styrofoam ball. It's called a pith ball, but more importantly than what it is what it's coated with. And it has sort of a metallic paint on the side of it. And as a result, it has the ability to pick up a charge or exhibit some behavior of a charge. All right? So, plastic rod, silk tie, okay? Charging by friction. As I move the plastic rod across the silk tie, electrons are transferred. I don't know which way is going which, all right? That's not important at this point in time, but, okay? So, as I bring the charged object, right, close to the pith ball, the first thing we see is that there's a little bit of an attraction there, right? Implying that they have an opposite charge, yes? Okay. Can you guys see that the way that it was? Right? Okay. If I take it away, the pith ball just falls back to where it was. If I bring the rod close, right, those two are attracted until they stick together just like that. Okay? But now that they've touched each other, there's another transfer of electrons. Okay? If I separate them, now look what happens to the pith ball, right? What's happening to it in relation to the rod? It's repelling, right? implying that now they have the same charge. Okay? There's another way that we can cause electrons to move, and that is through, where is it? Conduction. Okay? So, electrons are transferred by direct contact. We talk, and I think this is just right underneath. So, at the bottom of the outline on the first page, bottom of the outline on the first page, okay, you got Roman numeral 3, letter C, friction, charging by friction. What has to happen in order for something to charge by friction? They have to touch each other, but what has to happen as they touch each other? Movement, right? So charging by friction depends on movement, okay? As those two surfaces move across each other, those electrons are transferred, okay? But, depending on the materials, sometimes we don't even have to move them across one another. Sometimes we can just touch them and electrons will flow. That's charging by conduction. So, what's the key to charging by conduction? What has to happen? Contact, right? Direct contact has to happen in order for charging by conduction. So, charging by friction requires movement. Charging by conduction just requires contact, and those electrons will just flow from one object to the other. Okay? Depending on the materials involved, that determines which way the electrons flow. Some objects really want electrons, some objects are ready to get rid of them. Okay? One really good example of charging by conduction is what we refer to as grounding. Okay? Grounding is the transfer of electrons either to or from the earth by direct contact. Okay? Now, transferring electrons to the earth is a little different than transferring electrons to you or me. Okay? In a couple of examples that you did on Monday, you ended up with a shock. Yes? Okay? Shock is going to happen first when you come in contact with a charged object, right? But really what's going on there is those electrons that are looking, right? What do we know all electrons are trying to do to each other? They repel each other, right? And as a result, they're trying to get far away from one another, okay? There's no farther place they can go to spread out than if they go into the earth. The earth is like not infinite, but the earth is a big, huge object that electrons can spread out as much as they want to because there's so many atoms that make up the earth, right? Lots of opportunities for those electrons to spread out and get away from one another. When we ground something, what we're doing is we're giving those electrons that have been built up in one area by charging through friction or charging through contact to get away from one another, to give that chance to spread out and be away from one another. Okay? Is that good? Okay. So, one example of grounding that you guys worked or that you guys saw the other day was with the electroscope. Okay? So let's go back here. Let's move the pinball. And let's go back to the camera. Alright, so let's adjust this view here. It's a little crooked, but alright, so do we remember the electroscope? Yes? Maybe? Okay. So here, this is a metal rod. It's got a ball on top of it, and down inside of the electroscope, which are a little bit difficult to see here because of the thing, but there's two small pieces of aluminum foil. Okay? Maybe I should not block the screen so you guys can see it. Okay. So 2 small pieces of aluminum foil. Okay? Right now, everything's neutral, everything's cool, we're just laying there, right? These electrons, these little pieces of aluminum foil are just hanging straight down because gravity is causing them to hang straight down, right? Okay. So I'm going to put this piece of glass. The piece of glass is just there to keep the wind from blowing the pieces of aluminum foil back and forth, okay? All right, so rabbit fur, right? I take the rabbit fur and I rub it along the table, okay? What am I doing here? Charging by friction, okay? Where the rabbit fur is touching the table, we're trading electrons back and forth between the rabbit fur and the table, okay? So now, let's say, for argument's sake, and I don't know if this is the case or not because I don't really know the nature of the materials too much, but let's say that the table ends up with a bunch of extra electrons, okay? I take my metal handle and I put it down on the area that I was rubbing with the rabbit fur. There's not really a whole lot of place for these electrons to go. Maybe into this little aluminum piece, but there's really not a whole lot of space for it to go. But if I touch this, right, now the electrons have a chance to spread out even more because I am attached to the ground. This is charging by contact, but it's allowing these electrons to go all the way to the ground, right? This is grounding. Kind of, sort of, maybe? Okay with that? Okay. Now, in that process, okay, this aluminum piece has picked up an excess charge. All right? Let's see if this works, if I did it right, okay? Can you guys see the little pieces of aluminum foil? Okay. So, hold on. Can you guys see that they move when I bring it close? Can you guys see that in the video? All right. So, as I bring the little aluminum circle close to the electroscope, the aluminum foil leaves sort of push themselves apart. But when I bring it back, when I pull it away, they fall back down. Okay? Does it appear that those aluminum foil pieces are gaining a charge somehow, some way? Because what are they doing to each other? They're repelling each other, right? But then, when I take the aluminum circle away, they just fall back, and now they're not repelling each other anymore, right? Until I actually touch, right? Okay? And now, those aluminum foil pieces stay separate from one another. Now, they have gained a permanent charge, right? Or they've gained an imbalance of electrons. I don't know, you guys in the front row might be able to hear it. Did you hear the shock that when I brought the aluminum circle there, right? That's a transfer of electrons by contact from this aluminum side to the metal rod and the aluminum foil pieces, okay? Why are they separate from one another? Why do the little aluminum foil pieces separate? They have the same charge. They're trying to repel, right? What happens when I touch the ball on the top? Okay. What did I do there? That was grounding, right? Those extra electrons that were contained in the little pieces of aluminum foil were looking for a place to go. They went through my body into the earth. Okay? Give them another charge. Not quite as much charge this time. Do they still repel each other? Yeah, not as much as they did before though. Sammy, go ahead. Gotcha. So here, let's try this. Okay, let's see if this works. This is plastic, right? Okay, the handle this is plastic. I've never tried this before. This is completely the first time I've ever doing this. So if it doesn't work, don't yell at me. Okay. All right, ready? Okay. Did you see what happened or what didn't happen? Let me do this. Let me charge this back up again. Okay. right, ready? Okay, so now they're really charged up, right? They're really far apart, okay? Plastic side of this handle. Nothing happened, right? Okay? The ground provides a place for those extra electrons to go to spread out, but there has to be a way to get to the ground, right? In this case, the plastic handle doesn't provide a path for those extra electrons to get to the ground. Therefore, they don't go anywhere. Does that make sense? It's actually going to be such a great transition to the next part. So, yeah. But does that make sense? That if they don't have a way to get to the ground, they can't get there and they won't go anywhere. But if they do have a way to get to the ground, like through me, or actually through kind of along the surface of me, then they will get back to the ground and spread themselves back out. Okay?
So if you touch an electrical wire and you're just hanging there, not touching the ground, like the shock?
Right. Now, granted, touching an electrical wire, the electrical wire is coated in plastic, right? So it's not a place for them to go, right?
Yeah.
But if, let's say, I'm on a plastic stool, right, that doesn't provide a path to get to the ground, yeah, then you're doing okay, right? Now, if you're on that plastic stool, though, you are gaining charge, okay? So then what happens if somebody comes along and shakes your hand? That's a problem, right? Because now there is that path to get back to the ground, all right? So, what allows things to get to the ground and what doesn't allow things to get to the ground? Well, that gets us into the idea of conductors versus insulators, all right? So let's flip back to the front side and let's talk about Roman numeral number 2. Okay? So first, like their name suggests, what do conductors do? They conduct. Well, let's not use the word to define itself, right? What do conductors do in terms of charge? They transfer electrons easily, right? So, most metals are conductors. Why are most metal conductors? Sammy, it goes back to your question from before, okay? This picture here shows a bunch of electrons. These are all valence electrons, okay? In metals, what we'll find, especially when we get into our stuff next unit about bonding, most metals only have a few valence electrons, 1, 2, maybe 3. As a result, first, valence electrons are where in an atom? Outside, right? Most metals don't have very many valence electrons. And the ones that they do have, they don't actually hold on to that tightly. They're pretty willing to give those valence electrons away to other things. And so these valence electrons actually aren't attached to individual atoms or individual nuclei. They sort of have the freedom to move around and maybe it's connected to this atom every once in a while, but now maybe this one goes down here and maybe it's sort of connected to this atom. It's a real loose sort of connection between them. And as a result, electrons flow pretty easily through conductors. They transfer charge easily. So going back to this demonstration, right? Without a conductor, those electrons don't have anywhere to go. And so they can't get to the earth and spread themselves out, right? That obviously then leads us to the other one, right? An insulator, insulators don't allow electrons to travel freely between them, right? They hold on to valence electrons pretty tightly, so they aren't free to sort of move from atom to atom. If most metals are conductors, what kind of elements do you think are Insulators.
Non-metals.
Non-metals, right? Okay. That doesn't mean that insulators never can get a charge. It just means that they don't allow that charge to flow through them very easily. Okay? Good there? I think that's a good place for us to stop today. We'll pick up the other part tomorrow. We'll talk about Coulomb's law, and we'll talk about electric field. Okay? Good questions, though, everybody. It's like that flowed really nicely. I hope it made sense as we were talking. So.